What's up? What's up? It's your man, Jimmy Chan. All right, so today we're talking about conditional probability and general multiplication rule. So, conditional probability is the notation of probability of F given that event E has occurred. Okay, it's the probability that the event F occurs given that event E has already occurred. So, notice how this is written, right? So, be careful because in case if you do write it the other way, E given F, right? It's not bad for you to write it as P of E and F divided by P of F, okay? Just so that you guys can remember that these two are the same, right? So that you have these two are the same. That's number one. Number two, one of the things that you guys got to realize is that this right here and this right here means the same thing, right? F and E and F means the same thing, okay? You and me and you means the same thing, all right? So just be careful with that. But in terms of writing it out, it might help us to know what we're throwing in the denominator, okay? All right, so here, we're given this example. This looks very familiar, but the totals are already there for us, right? So A says, compute the probability that a randomly selected individual has never married given the individual is male. So we are finding the probability of never married given that's male, right? So that's what we're looking for. So if that's the case, then we're looking at the probability of never married and male over the probability of male. Okay? So what's the probability of never married and male? So probability of never married and male, right? So that's it right there. So that is 46 out of 260.1. And then the probability of male. Probability of male is right here. That's a really big number. So that's 126.9 over 260.1. Okay. So what is that going to give me? That's going to give me a probability of about 0.362. All right. Part B. What does B ask for? It says compute the probability that randomly selected individual is male given the individual is never married. So they want exactly the opposite way. So probability of male given never married. Okay. So I'm looking for a straight line. The probability of male and never married divided by the probability of never married. All right, so already notice that there's going to be some different numbers here, right? Although the first part is going to be exactly the same. This part is exactly the same. It's the denominator that's going to change. Never married, never married, never married. That is 86.1 over 260.1. Okay, so that is going to give me a different approximation, which is going to be 0.534. All right, so that's the reason why I say you might want to write it in this order so that you know what to put on the bottom, right? All right, to the next example, the general multiplication rule. So the probability of two events E and F both occur is the probability of E times the probability of F given that E has occurred. Okay, let's take a look. It says the probability that a driver who is speeding gets pulled over is 0.8. Okay, so probability of getting pulled over is 0.8. The probability that a driver gets a ticket given that he is pulled over is 0.9. What is the probability that a randomly selected driver who is speeding gets pulled over and gets a ticket? So I want to know the probability of pulled over and gets ticket. Okay? All right, so that means this is going to be probability of getting pulled over times the probability of getting a ticket, given that they're pulled over. Okay, what is the probability of getting pulled over? That is 0.8. What is the probability of getting a ticket given that they're pulled over? Well, that's what it says right there. Given that he or she is pulled over is 0.9. So that's going to give you, actually, this is going to equal to 0.72 as a probability. All right. How about this one? So this one was nice to us because like everything was kind of given to you. So it's a lot easier just to throw it in there, right? All right. So this one here, suppose that of 100 circuits sent to a manufacturing plant, 5 are defective. The plant manager receives their circuits, randomly selects 2, and tests them. If both circuits work, she will accept the shipment. Otherwise, the shipment is rejected. What's the probability that the plant manager discovers at least one defective circuit and rejects the shipment? All right, so there's 2 ways of looking at this. So let's look at the 2 methods. Method 1. Okay, method 1. If we look at method 1, then we would say, okay, I want to know the probability of at least one defective. Right? Okay. That would be the same as saying 1 minus the probability of none defective. Right? Which means this would be 1 minus the probability that the first is not defective. And then I'm going to multiply that by the probability that the second is not defective. Not. Given that the first is not. Okay? So that's what I'm looking at. So if that's the case, so 1 minus, well, since the shipment is 100, there's 5 of them that are defective, right? What is the probability that the first one is not defective? So there's how many of them? There's 95 out of 100 of them that are not defective. All right? So the probability that the second one is not defective given that the first is not. So if you picked one, the first one is not defective, there is still 5 of them that are defective, right? So if there's 100 of them, you picked one, there's down to 99. Your first one was not defective, so you did not choose one of these 5 that are. So there's still 5 defective ones in there, right? However, the total amount that you have now is only 99 circuits left, but 94 of them are still good because there's still a difference of 5 here that are bad. So that is where we would get this, and this will approximate about 0.098 probability that at least one is defective. Okay. All right. What is the second method? So you want to know method 2. Method 2 is kind of like a classical method that I like to look at. And saying, okay, what if we were to look at just, the outcomes are the same, right? You're going to pick 2. The first one can either be bad or good, right? For it to be good, it'd be a 95 out of 100, right? Because the first pick, there's all 100 of them, and there's only 5 of them defective, so 95 of them must be good. If you pick the bad, then you pick the 5 out of 100, right? And then you pick a second one, right? So it's either going to be bad or good. Okay, so let's assume that the first one was bad. So you picked one of the 5. Number 1, there's only 99 circuits left, and there is only 4 bad ones left, right? And if the first one was good, still you only have 99 circuits left, but assuming that the first one was bad, right? That means you still have all 95 good ones to pick from. If the first one was good, what was the chance of the second one? So if the first one was good, you're still down to 99 circuits to pick from. But the first one was good, so all the bad ones are still there, which is all 90. So there's 94 of them that are, sorry, not 94. There is still, it's assuming that the first one is good, the second one is bad, so there's still 5 of them that were bad. Assuming that the first one's good, right? Assuming the first one's good, there's still 5 bad ones in there, right? So this one here would still only have 99, but assuming the first one's good, I still have 94 of them that are good, okay? So if we look at this combination, we have bad, bad, we have bad, good, we have good, bad, and we have good, good, right? So if that's the case, to find these probabilities, we would go bad, bad would be 5 out of 100 times 4 out of 99. And then here will be 5 out of 100 times 95 out of 99. Here we have 95 over 100 times 5 out of 99. And here will be 95 out of 100 times 94 out of 99, right? So again, we're looking for the probability that at least one is defective, right? So at least one, if you look at least one, bad, bad has at least one that's defective. Bad, good has at least one that's defective. Good, bad also has at least one that's defective. Good, good is the only one that doesn't have any defective ones, so we don't choose that one. So that means here I would say, okay, that's equal to the probability of bad, bad plus the probability of bad, good plus the probability of good, bad. Okay, now why is it adding? Here's the reason why. Let me go ahead and bring this down a little bit and show you guys that. So this will be the probability of bad, bad, or bad, good, or good, bad, right? It's one of these possibilities are all possible, right? Because you're only testing 2 circuits. It's not like you're testing 6 of them. You're testing only 2. So one possibility is that you pick 2 bad ones back to back. Or you pick the first one bad, second one good. Or you pick the first one good, second one bad. Okay, that's why we add these. So what will happen is that these will come out to be 0.002, 0.048, and 0.048, which will give you a total of 0.098. So if you look at that, it looks really familiar right here versus right here, right? And the way I got these numbers here is actually putting this in the calculator. This is giving you 0.002. This is giving you 0.048. This is giving you 0.048. And this here is giving you 0.092. Now, another way of utilizing this is looking at as, okay, so let me keep the yellow here so that you can see where these are coming from. And then let me change this to red to show you about good, right? So I could also say that the probability of at least one would be the same as 1 minus the probability of them both being good. Okay, so none are defective, right? So it's 1 minus none are defective, so that means they're both good. So this would be 1 minus, and that number was 0.902, which will also give you 0.098 as well. Okay, so another way of doing it. So there's 3 methods right there. 2 of them are based on your so-called classical method, and 1 is really your empirical. Well, I hope that helps. If there's any questions, please let me know. See ya. Bye.